So make sure you have one copy of homework too. So I have placed it over there. The deadline is for this is next week on Thursday. So hopefully we can finish this very small, short chapter by next Tuesday. Previously I told you let's have a quiz on Tuesday class, but I think it's better to shift it to Thursday, given that we will have the homework done by that time, so you are better prepared for it. Okay? So next Thursday, due date of homework, and also you will have a quiz. So it's an in-class quiz, closed notes, closed book, so on chapter 9. So they are going to focus on the concepts. Okay, any questions? All right, so this is another example here. So we have a different binary mixtures. So in case A, methanol and ethanol, B, 1-propanol and 1-heptane, C, acetone and methanol, D, 1-propanol and 1-hexane, and we have some basically volume of mixing, right? So this delta V, basically what we establish is the mixture volume minus individual volume. Okay, so it doesn't tell you that they're considering either solution or anything, right? So we have these curves for different mole fraction of the component 1. So here component 1, you can think about this, basically this row is the component 1 in each mixture, okay? So can you tell me which one is that dashed black line close to 0? So we have 4 options, 4 mixture A, B, C, D. So which one do you think will be almost 0 delta V of mix, meaning that volume is not changing upon mixing?
Will it be mixture A?
Mixture A, why is that?
They look very similar in their bonding types, and they're quite similar in size too.
Yes. So you have both almost the same size, same shape. Both can create hydrogen bonds, so they are very similar to each other. So there's not much difference in them, right? So this corresponds to mixture A. So other ones are a little bit tricky to exactly say which one is the basically shows the decrease in the volume, and another one shows an increase in the volume, or you basically a continuous black curve over there shows both ways, right? So in one part it is increasing, another one is decreasing. So that's a little bit more difficult to say. So for the mixture B, it turns out always your volume of mixture is going to increase. So these two components, they pretty much repel each other. So kind of interactions are slightly different. So you have a hydrogen bonding OH group over there. In heptane, it's all hydrophobic. So always they are going to repel each other. In case C, so you are going to have negative delta V of mix, meaning that volume is going to decrease and all over the mole fractions that you have. So you can basically create hydrogen bond between the acetone and methanol. So that's the basically, if you want to look into the interaction, why this is happening. So you have an OH here, or you have an O over there, so they can interact with each other and basically create this small nanoscale domains, okay, that can fill the gaps. So the volume decreases. And in the case of D, interactions are more different because you have also OH group in one, and another part is the hydrophobic part when for 1-propanol is large. Okay, so that hydrophobic part can create hydrophobic attraction with the 1-hexene. So that basically gives the some part that you have the negative mixing volume, basically this side here, this side of the curve. So you have attraction between 1 and 2, okay? So definitely I'm not going to ask you to tell me which one is C, D, E, but for me, important part is you can identify which one is A. Okay, so meaning that there is no change in the volume. So you should be able to identify that mixture based on the molecular structure of your component 1 and 2. All right. So when I discuss the ideal solution property, so we focus on the volume, internal energy, or enthalpy. So you said, okay, you can easily write them as the mixture minus the individual one. Very similar to the mixing properties, right? But in the case of entropy and Gibbs free energy, something changes. So you cannot write as basically, if I define S ideal, so let's say I have component 1 and 2. What is the problem if I define it like this? So I have the mole fraction of component 1 and also 2. So both of them are going to add up to 1. So it's a binary mixture. And I have the pure component molar entropy. When I'm mixing them ideally, meaning that they are very similar in size and the shape, right? So two types of molecules that I have. But I cannot write the entropy of an ideal solution like this. So this is wrong. So that this is not going to work. But for volume, we did this, right? For volume works, for enthalpy works, internal energy is fine. So why is what is the reason? What do you think? So let's have this little experiment here. So think about, we have component A, that black circle over there. And we have also component B with a red circle. And this red circle can basically be placed in two basically positions. So that's our mixture, right? So, and component A also has two positions. Either it's going to be in the first square or the second square. So we have two ways to arrange that molecule, let's say, in component 1 and component 2. Do you remember what was the definition of the entropy? What was the definition of entropy? Yes?
Number of possible microstates.
Exactly. So number of possible microstates, right? So these are my microstates. For black one, I have two microstates. I can either put it over in the left square or right square, right? So for entropy, we said it is going to be equal to a number of the microstate available for our system, okay? How many ways that we can arrange it? That is that omega. Because this omega is a large number, so we have this ln omega, and make the dimensions fine, we put Kb, Boltzmann constant over there. So that's the equation that gives us the entropy that we know. So I have system A. What is the entropy of that system? So I will write it as a S black. So this is just a pure, so I haven't mixed them. So they are separate. So it's just going to be Kb, ln. How many ways that I can arrange it? That's black, 2, right? ln 2. Similarly, I can write the same thing for the red, right? There's nothing different. So for red one, I have also two positions. So it's going to be Kb, ln 2. Okay, so if I follow what I wrote here, let's call that what our intuition says, right? So it makes sense. I'm adding things up. There's no difference between them. So this S of ideal mixture that I have here, so let's say now I'm putting system A and 2 in one big container, right? And I'm just summing up the individual entropy. So this is going to be what? Kb ln 4. that's my S ideal. And if you calculate, let's say, if I calculate the delta S during this process that I have gone from pure to the mixture, right? The mixture that I have created. So this is going to be, let's call it delta S ideal. So it's going to be KBlN4 minus the individual ones, right? The pure component one, which was it? KBlN2 plus KBlN2, right? What is that? 0. There is a big issue in my argument here. There's an issue here. Individual components are fine. So I have only 2 microstates. But once I'm mixing them together, so basically each subsystem has 2 positions, right? So let's look at this. How many microstates I have? These are the microstates I'm going to have. The number of ways that I can arrange them is not going to be just 2 plus 2. So I can have 4. Basically, I can put first one as a black circle, second one red, and empty, empty. Then I can basically play with this permutation that I have here. Okay? So your number of the microstates significantly increases as you mix 2 things together. So it is not linearly additive. So entropy is not additive. Okay? So we are not going to discuss the details of this calculation. Even in your book also, we don't have the basically mathematics of that, but you can use the probability theory to argue that the number of the microstates or the omega increases as you mix things together. And this goes beyond the linearity. So, yes, it is raining. Yeah. So the flaw in my argument that I presented was that I was not calculating the omega in my mixture properly. I was just adding them up. Okay? So that was the issue. So we are not going to talk about how we get this formula for x1, ln x1, but you just assume it that this part. So if I want to mix 2 things ideally, I will have the individual, basically pure component. This is like any other type of property. And I will have the increase in the entropy that comes from the mixing. Just process of mixing. So those logarithmic part, and you can now think about that we had ln of omega, so that basically emerges here. So this part comes from mixing. So r times x1 ln x1 minus r times x2 ln x2. Okay, so that's a very important equation here. So if you increase the number of the components more than 2, that's fine. You're just going to put it in a sigma that runs from I to n, where n is the number of the components in the mixture. Okay, so n and this is mixing ideally. So when you are mixing 2 things ideally, your entropy is going to increase compared to the summation of the pure cases. This was not the case for volume. This was not the case for the energy, for internal and enthalpy, right? So do you see that entropy increases here in this equation? I have a negative sign over there, right? I'm subtracting something from the pure component, right? How come it is increasing?
The natural log output a negative.
Yes. So you are calculating natural log of a number between 0 and 1. That is negative. Okay? So that is negative. So you have a kind of a hidden, basically, minus sign inside that, right? So that is the total, basically, part here we have. This part always is going to be a positive number. So that is a positive number. Any questions about this? So this is very important. The most important part of this chapter is this equation. So now how do you define the excess entropy? What was the excess property definition?
It's when there is a difference from compared to the pure components.
That is mixing property. So don't confuse these two things together. When you are considering an excess property, you are considering the difference between the real mixture and ideal mixture. So, in case of excess entropy, I'm going to write it as a S minus S ideal. Okay? So I don't know what is S, so it can be anything. It's a real mixture. I don't have information about it. But I know what is S ideal. So that is basically in the parentheses here. I have basically replaced the equation that I had. And for a binary system, you can open it up and write it like that. Same thing that you can do for GXS. And this also the same reason that G is not additive when you are mixing two things together, because it involves entropy. All the parameters that involve entropy, they are not additive, right? So for GXS, you define G minus G ideal, and understanding that this G ideal is defined as H ideal minus TS ideal. Okay, so you remember G was what? H minus TS. It is ideal or excess, doesn't matter. So you can do that. So if you replace those things, so you will have the expression for GXS for your mixture. So this is also a very important relationship. We will come back to this when we are talking about non-ideal behavior in chapter 11. So we are going to use that expression. Over there I will ask you, so what was the basis of this equation, right? So where did you got it? So it's about the entropy, entropy of mixing those terms, Xi, ln Xi. Any questions? Okay, now how do you define the mixing property? So I'm going to ask this several times. Excess property, mixing property, because I'm going to introduce another parameter in a few minutes. How did we define mixing property? With delta, big delta. This was excess. Excess always is between real mixture and ideal mixture. Real mixture and pure component. The difference between the real mixture and the pure component is going to be the mixing property. And that's the definition. So if I want to define delta S, it's going to be a real mixture minus X1, S1 plus X2, S2. This is for a binary mixture, and if I have more, I will just keep adding things, right? So do you see now the difference here? That's very important. It shows the difference between the initial condition where things were separate from each other, two pure components, and when they are mixed. So if I ask you what is delta S ideal, can you tell me what is that? If you're mixing things ideally. Do you have any information about your mixture entropy? If you are mixing things ideally? Same formula, right? You are going to use that formula over there. What is S ideal?
Can we just plug in the equation?
Which equation?
Like the one that shows how the entropy of each pure component, and then
There is a log term, right? So entropy of, yes. So S ideal, S ideal minus so S ideal is x1 S1 plus x2 S2 minus R x1 ln x1 minus R x2 ln x2. Then I have minus x1 S1 plus x2 S2. I'm going to be left with minus R x1 ln x1 minus R x2 ln x2. Okay? Stop me if you have a question, okay? So if you don't stop me, I will go fast. So you need to be able to distinguish these two types of properties that we define. One is the basically excess, real, minus ideal case. Another one is the change of that property upon mixing. Always we consider the pure component as a reference point. So similarly, you can define delta G ideal. So make sure you do this when you review this lecture. So I'm just going to write the final equation, but try to derive it, okay? And let me know if you have any problem with that. It's going to be RT x1 ln x1 plus RT x2 ln x2. And these are for systems that they have two components. If you have more components, you will have more terms, basically RT x3 ln x3. So you're not worrying about them now. So to summarize it here, basically this is a table that it shows that the property of an ideal solution, mixing property for an ideal solution, for enthalpy, internal energy, volume, the mixing property all is going to be 0. But for entropy, it's a non-zero, as I showed you for the entropy. So you can derive it for the Gibbs free energy and for the real mixture for excess properties. So always you are considering that basically compared to the ideal solution. Whatever you have for the ideal solution. Okay, real mixture minus ideal solution. All right, so this is okay so far, but it's a little bit, so we have this excess properties that are pretty useful when we are talking about the non-ideal behavior, but still we are always motivated by the ideal solution property. Let's say I have H ideal for a binary system. It's very convenient to write it like a x1 h1 plus x2 h2, right? So I can relate it to the pure component properties. Now I'm looking for a very specific property. I'm going to use overlap here. And property of my real mixture, not ideal. So I'm not putting any constraint here on M. M is just a molar property of my real mixture. And I would like it to write it as, let's say I have a binary mixture, x1m1 plus x2m2. It is so convenient, right? So I'm going to find out what is the rule for these properties, okay? So these mi's are called partial molar property. In this case, it's component I. And one example that you can think about, if let's say I have a volume of mixture, right? So I would like to write this volume of mixture like x1 v1 bar plus x2 v2 bar. Unit-wise, it is basically same as the molar volume that you have, right? So you see that unit should match, right? So I would like to design some property like that. So this is the most important part of the phase equilibrium thermal, to understand what are these partial molar property, because we are just going to calculate different partial molar property for different types of equilibrium that we are going to consider, okay? So it is very important to get the physical understanding. What does it mean? So here I have the basically very rigorous mathematical definition of it. So I will show you what is the physical meaning of it. So this is defined as the derivative of a basically solution property M, and that derivative is extensive property. So I have written it here as Nm. So derivative of this property, whatever you are considering, total volume, total energy, total entropy, with respect to the other, basically respect to the change in the number of the moles of that component I, D and I, holding other moles constant and holding temperature and pressure constant. So we define it like this. And once we define it like this, you will see that it's going to satisfy this requirement for me, and another one which is very important, you will see that. So that basically, I'm going to show you how you are going to get the basically a mole average of a property from partial molar properties using that definition, okay? If I have a binary mixture, I will have two partial molar properties. So first one, it is the derivative with respect to N1 that will going to give me M1. I'm going to hold constant temperature, pressure, and N2, okay? And M2 is going to be dNm, dN2, temperature, pressure, N1 constant. Okay, that's how we define this. So this is that equation. So these are called partial molar properties. What do they mean? Physical interpretation. So any idea what is the physical interpretation of this? Partial molar properties. Let's say if I had the volume, right? So if I go back to this volume example over there, it tells me that the volume of my mixture is going to be the mole fraction of component 1 times some molar volume plus mole fraction of component 2 times some molar volume of the component 2. So these are not that usual molar volume you expect. So you can think about in this example for the volume, these are effective molar volume when you mix things. Okay? So think about it. You have a container, component 1 and 2. Red is component 1, blue is component 2. So what I'm going to do, I'm going to add a little bit of component 2 to the mixture. Okay? So that's the cartoon that I have. Let's say I'm adding, this amount that I'm adding is delta N2. I'm adding it to the mixture. So it's a tiny amount. Okay? So what will happen? The volume will increase, right? Because let's say, or it is going to change, not say increase necessarily, right? So if I do it ideally, delta V of ideal, basically I have an ideal solution here. And if I know what are the molar volumes of the component 1, let's say V1, molar volume of 1, and V2, molar volume of 2. Can you tell me how much is the change in the volume? So I have V1, V2 molar for pure component. I'm adding some amount of mole. How much is the volume I'm adding over there? It is going to be the number of the moles that I am adding times the molar volume of that component, right? So this is the volume that I'm adding to the system. So it is just going to be V2 delta N2. So this is my ideal solution law. In the real case, what you have, we can write it as a V2 bar effective times delta N2, because you know that volume is not going to change based on the ideal solution. So that's the idea. So if I want to calculate now V2 effective, I need to calculate delta V divided by delta N2. And in my experiment, I'm not changing temperature, I'm not changing the pressure, so volume is just only changing due to the addition of that component. So that's the meaning of the derivative here. So do you see now the derivative here? So if I have it a very tiny amount, my V2 effective, the molar volume, effective molar volume of the component 2 is going to be derivative of V, derivative of N2. I didn't change N1, I didn't change temperature, I didn't change pressure. That's what? That's the partial molar volume, right? So that's basically what we defined it as to just avoid this confusion between the effective volume and etc. So we are using overbar. So that's the physical meaning of it. Effective molar volume in the mixture, or effective molar property in the mixture. It can be anything. Are you okay with the definition, the meaning that it has? Okay, so that is very good. So now let's see one example. So we want to add methanol to water to create an anti-freeze mixture. We are asked to prepare 1 liter of antifreeze solution consisting of 20% methanol in water. Okay, so, and we must calculate the volume of the pure methanol and pure water to be mixed at this temperature of 50 C to form this 1 liter antifreeze. So what information we have here is the pure component molar volume and also the partial molar volume that corresponds to this experimental condition that we have. So think about it for a minute, then try to come up with a strategy to solve this or estimate this volume of the pure methanol and pure water. Any idea where we should start? Can you calculate the molar volume of the mixture? What do you need to calculate the molar volume of the mixture? If you want to write an equation, give the molar volume of the mixture in terms of the mole fraction, what is that relationship? We just had it here, right? So for the property of mixture, always it's going to be mole average properties we consider in the partial molar properties. So x1, n1 plus x2, n2, where n1 and n2 are partial molar properties. So for volume, it's going to be x1, v1 bar plus x2, v2 bar. Okay? So if I use that, so if I call methanol as component 1, so water as component 2, so my V of mixture is x1 V1 bar plus x2 V2 bar. So that's the molar volume of mixture. And I can calculate that because I know my x1 is 20% and x2 is how much? 80% in the mixture, right? So let's say I have this basically N1 plus N2 gives me this total number of moles, N. So you are basically mixing two streams, 1 and 2. So if I consider that 0.2 times 39.34 plus 0.8 times 18.1, I'm going to have 22.35 centimeter cube per mole. Okay. So this is a molar volume of my mixture. What else I have? We want to create 1 liter, right? So that's the total volume of our mixture. What can we calculate here? Remember, your goal is to calculate the volume of the pure components. For calculating the volume of pure components, what do you need here?
We need to use the mixture properties.
No. For calculating the pure components volume, you have the molar volume. You just need to know how many moles do you have, right? For component 1 and 2. Because once you have that, then you can calculate the volume, right? So what I'm going to do now, I'm going to calculate the total number of moles, because that is going to be conserved, right? So N is my total number of moles, is the total volume that I have divided by molar volume. Does it make sense? So total volume is 1000 centimeter cube. So that is 1 liter divided by 22.35 centimeter cube per mole. So I'm going to have 44.74 moles. Now, can you tell me what is the N1 and N2? N1 is the number of moles of methanol. N2 is the number of moles of water. So you have the total mole, number of moles in the mixture. You have the mole fraction in the mixture, right?
Yeah, so the amount of moles of ethanol will be 20% of the total moles.
Yes. So for methanol is going to be 20% of that. So 20%, basically 0.2 times total number of moles that we have, 44.74, 8.95, and N2 is going to be 80% of that, is going to be 35.79 mole. And using these two numbers, I can calculate V1 and V2, which is the pure component volume, right? So if I follow that, my V1 is going to be 376 centimeter cube, and V2 is 652 centimeter. Is it 652? Yeah, centimeter cube. That's the individual ones. So this is how you can basically distinguish between the real mixture volume and the ideal mixture, right? So if you look at it now, if you just sum up V1 plus V2, what is that number? Should I do 1 liter?
Oh, wait. No, it's more than
That's the whole purpose of
Yeah,
what I
sorry.
have discussed,
It's
right?
more than-
It is not going to get to 1 liter. That's the main thing. Moles always are conserved, right? So because there's no reactions happening here, it's just you're just mixing. But volume is not conserved. I can ask you, what is the volume of mixing here? or what is the excess volume? So these are the different questions that I can ask in the same line, right? So I can ask you, what is the mixing volume here? So think about that. What is the excess volume of this mixture? So you should be able to determine that one too. So think about these two basically follow-up questions. Any questions? How we did this? Are you okay with it? Okay. So then we have some concepts of infinite dilution. So in the table I have here, the first column is the mole fraction of ethanol. So there is a mixture of ethanol and benzene at a temperature of 318 Kelvin and pressure of 1 bar. Second column is the mixture enthalpy at different mole fractions. So basically I have a mole fraction, let's say 0.26 of ethanol. So I can measure the total enthalpy of my mixture. And from some magical relationship that I'm not showing it here, I have the partial molar properties, basically partial molar enthalpy of this mixture, given the H1 bar and H2 bar over there too. So the next two columns are the partial molar properties. Okay, so when the mole fraction of a component in a binary mixture, let's say I have two components, approaches 1, right? So let's say X1 goes to 1. H1 should approach to what? What do you think?
It'll approach H.
Okay, good. Because we know your H of mixture is X1 H2, right? So if X1 goes to 1, X2 goes to 0, right? So X1 plus X2 adds to 1. So I have this, right? So H1 should approach to H value you have. And same thing you can say for X2. So when X2 goes to 1, your mixture property should be the pure component, because you are not going to have a mixture anymore. It's a pure component. That's the idea. But one thing interesting that happens is that when X1, let's say it goes to 0, we consider that case, what happens to H1? So that particular case, we call it an infinite dilution case for component 1, meaning that there is a tiny bit of component 1 in the mixture. Okay? The contribution, the molar contribution to that property that we're considering here is as an enthalpy, is going to be named as infinite dilution property. So we are going to use this superscript infinite to distinguish that. It's very important. So if you look at the table here, as X1 goes to 0, so you have a finite number for H1 bar. So that's the infinite dilution for the enthalpy of component 1. Okay, so this is H1 infinity. And same thing that you can say as you X2 goes to 0 here, you have H2 infinity. Okay, so these are the two two boundaries that we basically distinguish the specific name. Any question about this? It's just the definition that we give. Okay. So if you plot it, so basically I'm putting the same data on a plot. So on the y-axis I have the enthalpy versus mole fraction. So this is my blue curve is my enthalpy of the mixture. So this is my H. So this is the red one is H bar 1 and H bar 2. Basically, this is the benzene that I have, okay? And you can see at this point, I have H1 infinity, and at this point, I have H2 bar infinity. That's the infinite dilution. So you should be able to identify those things on the plots. So these are the two limiting cases. Again, this is very important when we are talking about the non-ideal behavior in chapter 11. So it helps us to get the parameters for the some activity coefficient that we are going to define. Okay, so now let's a little bit chat about the mathematical framework that I introduced. So why it works, right? So why that definition of the partial derivative for component I, with respect to changing the number of moles of component I, automatically satisfy that relationship where molar property of mixture is just going to be x1, m1 plus x2, m2, and so on and so forth, right? So why this is the case? So think about you have a property in your mixture. It can be anything. So I'm calling it M. N is the molar, and I'm multiplying it by N to make it extensive. N is the total number of the moles. So this property is going to be a function of temperature, pressure, and the number of the components mole, right? N1 and N2. So you can think about the total number of moles are N equals N1 plus N2. So let's say we have two components, right? So if you have that basically functional form, okay, and you don't know anything about thermal, you should be able to write that differential form in this second basically line. So it shows the change in the, basically, this property, this extensive property that we have in terms of the change in the pressure, temperature, N1 and N2, because those are the variables that we have identified over there, right? So, and you are going to have coefficients of the partial derivative. So I have T here, so I should have dt, dp, dn1, dn2, and the coefficients are going to be partial derivative with respect to that parameter and holding the other ones constant. So that comes from the calculus, right? So first one, I'm calculating with respect to temperature, pressure, and all moles of other components, I'm calling Nj, are constant. Second one, I'm calculating the derivative with respect to pressure. Third one, with respect to N1. Fourth one, with respect to N2. And if I have more components, I'm just going to add more N's over there, right? Does it make sense? Any questions so far? All right, so the way that we have defined partial molar properties, I can see that this is M1 bar, and this is M bar 2, right? So that was the starting point. That is proposed, that definition. So I'm going to replace that over there to write it more compact. And I know from the change in the total property, d and m, is going to be n times dm plus m times dn. So that's the multiplication rule for derivatives, right? And I will do some basically manipulation over there instead of writing it in terms of the n1 and n2. So I'm going to hold it basically, instead of n1, I'm going to write as n times x1 and n2, n times x2, because it's more convenient to work with more fractions. Okay? So I'm going to replace that and expand that derivative, right? So dn1 is going to be dnx1, and again I have a multiplication rule, so I have two terms, so I need to cancel it. So that's the idea. So I'm going to replace everything in that basically second equation here. So basically I'm going to use it here. Any questions so far? All right, so if we do that, and so here I have it step by step, and I'm collecting also some terms. So, okay, let's see, yeah. NdM plus mdn equals to that whole derivative. So in the second part, I added the x1. So I can collect terms in terms of dn, and I can have terms in terms of n. So I'm separating these two. Okay. So I know dn cannot be 0. I'm changing the number of moles. I know my number of moles is not 0. Okay? The only way that this equality can hold is that each of these coefficients at the same time should be 0 to give me non-trivial solution. If n is 0 or dn is 0, it is a trivial solution that I have. I'm not looking for that. So I'm looking for non-trivial. So this coefficient is going to be 0. This whole coefficient is going to be 0 too. So look at the first coefficient. If you basically collect the term over there in that first row over there, you will get that. That's the outcome we predicted first. By definition, that is going to satisfy for us. Right? So this is just m equals x1 m1 bar minus x2 m2 bar. That should be 0. The whole thing should be 0. And we have this interesting one for the second one, which is the top one. Okay? So, I'm not interested, what's that? I'm not interested in deriving this. You should be able to follow it. Okay, so you have the details of it in your book, but the outcome is very important. You should remember the first one and the second one. So the second one is called Gibbs-Duhem relationship. It's a very fundamental relationship in phase equilibrium. And you can see that if you are considering constant pressure and temperature. Let's think about that. If you have a constant temperature pressure condition over there, what is going to happen? x1 m1 plus x2 dm2 is going to be equal to 0. You should remember this one. So this equation gives you the relationship between the partial molar properties in M1 and M2. And I don't need to know anything about the molar property. Just mole fraction and M1 and M2. Second equation gives the information about the molar property of mixture. M equals to x1, M1 plus x2, M2. Okay, so these are the two main conclusions of this partial molar property. So the first one is very important because I can multiply this or divide it by dx1. So let's do that. So it's going to be x1 dx1 plus x2 dx1 is going to be 0. You can do the other one, right? So you can divide it by dx2, doesn't matter. One of them. It's very important now. It's a differential equation. Remember how you solve differential equations, right? First order differential equations. So if you have an expression for one of the partial molar properties, if it is a binary mixture, constant temperature pressure that you are doing the experiment, you should be able to use this relationship to get the other one. Okay, so that's the importance of the Gibbs-Duhem relationship. You don't need to have information about the molar property of the mixture. Just one of them is enough. One partial molar property is enough. So in case of binary mixture also you can combine these two things and have a kind of a shortcut relationships to calculate these partial molar properties in terms of the derivative of the molar properties of your mixture with respect to component 1, dx1. Okay? These two relationships, I don't memorize them, okay? It works only for binary mixture, right? So it is kind of a conclusion of it's a derivation of for binary mixture. So if you have a ternary mixture or four-component mixture, it is not going to work. Only two components, okay? So you can quickly calculate the partial molar properties for component 1 and 2, okay? So let's see whether we can solve this example. So I can show you one example. So we have the enthalpy of a mixture for cyclohexane and benzene based on that relationship that relates the enthalpy to the mole fraction. Okay, the constant temperature, pressure. Temperature is 25, pressure is 1 bar. So benzene is a component 1, and cyclohexane is component 2. Okay. So we would like to calculate what are the molar enthalpy, partial molar enthalpy of the benzene in this mixture when it is equimolar at 25 C and 1 bar. So equimolar means what? We have an equimolar mixture. 50%, right? So meaning that x1, so for part A, x1 equals to x2 equals to 0.5. So that's the definition of equimolar, same mole fraction. So the way that I do usually, so maybe it's a little bit tedious, but it works pretty well. So I'm interested to calculate in this case, H1 bar, right? So let's write the definition. It's the dNH dN1 constant N2 and temperature pressure, right? So expression is given us at constant temperature pressure already. So that's the definition. So I'm going to basically build that expression in the parentheses, N times H, okay? So what is N? Is the total number of moles, right? I'm calculating the derivative with respect to N1, right? So what I'm going to do, I'm going to write this as N1 plus N2 times H Okay, because n itself depends on n1. Do you see that? So I need to consider that part. So I'm just going to write that. So let's see what is n1 plus n2 times h is in our mixture, right? So I will have n1 plus n2. So this is the expression for the h, right? So I'm going to just copy it from there. 3399 plus 4516. Instead of x1, I'm going to write it in terms of n1 and n2. So how can you write x1 in terms of n1 and n2? x1 is the mole fraction of component 1. What is it? Mole fraction of component 1 when you have n1 moles of the component 1 and n2 moles of component 2. N1 divided by N1 plus N2, right? Is it okay? Okay. So instead of X1, I'm going to write N1 divided by N1 plus N2. Then I have this coefficient, N1 divided by N1 plus N2 square. Right? That's it. That's the extensive property that I have built. Extensive enthalpy of mixture. What is the unit for this? What huge thing that I have written on the right hand side?
Molar enthalpy.
It's the molar enthalpy? It's per mole?
Partial molar.
It's a partial molar? What is the difference between the unit in the partial molar property and the regular molar property? Okay, my question is, what is the unit in the right-hand side of this equation? Options, joule per mole or joules or kilojoule, doesn't matter. Energy versus energy per mole.
Just joules.
Yeah. It's equality, right? So the units of this side and this side, they match. So H is molar per mole, energy per mole. I'm multiplying by moles. So it's going to be units of energy. So whatever energy we have, okay? So once you build this extensive property here, then in step 2, so let's call it 1. So I'm going to build this extensive property because I need it here to calculate the derivative. And second step is just calculate that derivative, right? So H1, so I'm going to just rewrite this. So now you tell me what would be the derivative of that. What we are calculating here is the derivative of that expression with respect to n1. Okay, do you remember the derivative that you used to calculate? Calculus. You are dealing with fractions here, right? So review this stuff, right? So I'm just going to, N2 is just a constant. That's the rule that I have. And I don't care about temperature, pressure. It's already embedded in those constants that I have. So only you are calculating the derivative of that right-hand side with respect to N1. So that's what you need to do. So if you do the calculation, so this is going to be minus 33.99 plus 45.15 minus 32.15, and I will have a term that comes from this fraction that I have. So if I write it a little bit cleanly, so that's my partial molar enthalpy for component 1. Okay, but still I'm not there yet because I have expressed based on the moles of N1 and 2, and it's always good to cast it in terms of the X1 and X2, okay? Because we are interested in the mole fraction. So, any suggestions to turn this equation to the mole fraction? So basically we need to figure out what is the parenthesis, right? Inside that parenthesis. So what I'm going to do, I will write it as, let's say, if I write it cleanly, this is basically n1 squared plus 2n1 n2, right? So because they are canceling each other. So I have 2n1 squared minus n1 squared, so it's just going to be n1 squared, right? So I'm going to write it as n1 squared divided by n1 plus n2 squared plus 2n1 n2 divided by n1 plus n2 squared. Do you see the mole fractions now? How did we define x1 and x2? No. We are not inserting any numbers now. Get the expression first. So the first one, the first term, n1 squared divided by n1 plus n2 squared, it is just x1 squared. Second term is what?
Is it x1 times x2?
Yes. Okay, so that's basically your third step. So this is the second step, that you calculate the derivative, then you basically convert that derivative components in terms of n1 and 2 to x1 and x2. So you go backward. And you can do the same thing for the component 2, right? Always you are inserting the number at the end for the x1 and x2 equal to, let's say here, 4.5. So it's going to give you a number here, right? So you can calculate that. That's not a big deal. The key point is you go step by step. Make sure you first build that extensive property. So n1 plus n2 times the molar property that I have given you. Then you calculate the derivative with respect to the n1 or n2 if you are interested in n1 or n2 bar, right? So the partial property. So they should be consistent. And when you calculate that derivative, make sure the other parameters in your expression is constant. In that expression, when I wrote it like that in the first line, the only parameter is changing when I'm calculating the derivative is the n1. Okay? So the expression that you are making over there shouldn't have n in it. It should be summation of the n1, n2, n2, whatever it is. So don't make that mistake, because n is not an independent parameter. It depends on the N1 and N2. Okay, make sure you review this for next class. So we will talk a little bit more about this, and I will give you another way to calculate this molar property, and we will discuss the same thing for gas mixtures. So that summarizes our chapter 9.